Imagine standing on a launch pad at dawn. In front of you, a silver skyscraper of metal and fire, a spaceship capable of clawing its way out of Earth's gravity well. In a few minutes, hundreds of tons of steel, fuel, and fragile human life will be hurled into the vacuum of space, and almost everything has to work perfectly the first time. In movies, spaceships glide silently, turn on a dime, and jump to hyperspace with a flick of a lever. Reality is harsher, louder, and honestly, way more impressive. Every bolt, every wire, every line of code on a real spacecraft has been tested, simulated, and argued over by teams of engineers for years. In this video, we're going to peel back the fairing and see what's really inside a spaceship. How do we launch them, power them, steer them, and keep people alive inside? And what would it actually take to build a starship that can leave the solar system for good? Before we dive into warp drives and sci-fi concepts, we need to nail down what a spaceship really is. Technically, engineers talk about spacecraft, machines designed to operate beyond Earth's atmosphere. That covers everything from tiny CubeSats the size of a shoebox, up to crewed vehicles like NASA's Orion or SpaceX's Starship. A true spaceship, in the popular sense, usually means a craft that can carry humans through space, potentially for long durations. That means it's not just a rocket with engines, it's also a life support system, a power plant, a navigation computer, a radiation shield, and increasingly, a reusable vehicle that can be launched, landed, refueled, and launched again. We'll start with how we get off the ground at all, move through propulsion and life support, then look at reusable starships and eventually interstellar concepts. Along the way, I'll contrast movie spaceships with the machines we're actually building right now, and the ones on drawing boards for the next century. Let's start with the brutal part, escaping Earth. To reach orbit, a spaceship needs to be going about 28,000 kilometers per hour sideways, not up, sideways, so that it falls around Earth instead of back down to the ground. That takes an enormous amount of energy. The workhorse technology here is chemical rocketry. You burn fuel and oxidizer, produce superhot gas, and throw that mass out the back at high speed. By conservation of momentum, the rocket moves forward. The problem is, fuel is heavy, and you need fuel to lift fuel, which leads to the infamous rocket equation. That's why rockets are mostly giant tanks with a relatively tiny payload on top. Multi-stage designs, where empty tanks are dropped during flight, let us shed dead weight as we climb. Every modern crewed spaceship, from Apollo to Dragon to Shenzhou, has depended on these towering launch vehicles to punch through the atmosphere and deliver the spacecraft where space actually begins, in stable orbit. Once you're above most of the atmosphere, the physics changes. There's no air to push against, no wings to generate lift, and almost no friction. Thrusters become your only way to turn, speed up, or slow down. This is where orbital mechanics rules everything. To change orbits, you don't fly like an airplane. You perform burns at very specific points in your path. A short burn at the right moment can shift you from a low Earth orbit to a trajectory toward the Moon or Mars. Spaceships use reaction control systems, small rocket thrusters placed around the vehicle, to rotate and fine-tune their motion. More advanced craft may use ion thrusters for very efficient, low-thrust acceleration over months or years. In space, every kilogram of propellant matters, so navigation is a careful dance of math and restraint. The most efficient spaceship isn't the one with the biggest engine, it's the one whose pilot and guidance computer knows exactly when not to burn. Let's zoom in on propulsion because this is where sci-fi and reality start to diverge. Chemical rockets are fantastic for brute force launches and quick maneuvers, but they're horribly inefficient for long journeys once in space. One step up is electric propulsion, ion or Hall effect thrusters. These use electricity, often from solar panels, to accelerate ions to extremely high speeds. The thrust is tiny, like the weight of a sheet of paper, but it's continuous. Over months, that adds up, allowing probes like Dawn to visit multiple asteroids. Beyond that, there's nuclear thermal propulsion, where a nuclear reactor heats hydrogen propellant, and nuclear electric, where a reactor powers high-efficiency electric thrusters. Both promise faster trips to Mars and beyond. On the more speculative side, we have fusion drives, antimatter engines, and even beamed sail concepts like breakthrough Starshot, which would push ultralight probes with laser light. These could get us to nearby stars within a human lifetime if we can solve massive engineering and safety challenges. Raw propulsion is useless if your crew doesn't survive the trip. A human-rated spaceship is basically a miniature ecosystem taped to a bomb. Inside that pressure vessel, you need Earth-like conditions: breathable air, drinkable water, comfortable temperatures, and protection from vacuum and radiation. Modern life support systems scrub carbon dioxide using chemical absorbers, recycle some water from humidity and urine, and carefully control temperature. The International Space Station is our best current example, a continuously inhabited spaceship where closed-loop systems are being tested and refined. For deep space missions, we'll need far more efficient recycling, including regenerative life support that can reuse over 90% of water and air. That might involve bioregenerative systems, plants, algae, or engineered microbes helping to close the loop. Every kilogram of supplies you don't need to launch means room for more instruments, shielding, or passengers. Designing life support is less glamorous than giant rockets, but it's absolutely central to any serious spaceship. Space is a radiation bath. Cosmic rays and solar particles can slice through human tissue and electronics alike. For short missions in low Earth orbit, Earth's magnetic field and the spacecraft hull offer some protection. But for long trips to Mars or beyond, shielding becomes one of the hardest design problems. You can add physical shielding, thick aluminum, water tanks, or specialized plastic composites rich in hydrogen, which is good at stopping high-energy particles. Some concepts even wrap crew modules in fuel or wastewater to double-use mass. Another approach is storm shelters, small, heavily shielded compartments where the crew can hunker down during solar flares. Electronic systems, too, must be radiation hardened. That's why space computers often lag behind cutting-edge consumer chips. They're built for reliability, not speed. There's ongoing research into active shielding, magnetic or plasma fields to deflect radiation. But for now, real spaceships protect their crews the old-fashioned way, with lots and lots of carefully placed material. Every spaceship is a power puzzle. In orbit near Earth, solar panels are the clear winner, cheap, reliable, and well understood. Modern spacecraft unfold sprawling wings of high-efficiency solar cells, tracking the sun as they orbit. Farther out, sunlight fades. By Jupiter, you're down to about 4% of the light you get at Earth. That's where radioisotope generators, RTGs, come in. These use the heat from radioactive decay, usually plutonium-238, and convert it into electricity. Probes like Voyager, Cassini, and Curiosity rely on RTGs for decades-long missions. Future high-power spaceships, especially those with nuclear propulsion or artificial gravity, may use full-scale fission reactors. That raises big questions about launch safety and in-space assembly. Inside the spacecraft, power management is a constant balancing act between life support, propulsion, communications, and instruments. Unlike on Earth, you can't just plug in more. A well-designed spaceship is an exercise in ruthless electrical budgeting and redundancy. Spaceships need brains. Guidance, navigation, and control (GNC) is the nervous system that keeps a spacecraft pointed correctly, on course, and stable. It fuses data from star trackers, gyroscopes, accelerometers, and sometimes GPS for near-Earth missions. Star trackers are especially elegant, small cameras that look at the sky, recognize constellations, and determine orientation by comparing them to an onboard catalog. It's cosmic navigation by stargazing robots. Control algorithms then fire reaction wheels, control moment gyros, or thrusters to rotate the vehicle. For crewed missions, hand controllers in the cockpit usually send requests to this system rather than directly controlling engines. The computer smooths everything out. Autonomy is growing more important. Deep space missions can't wait minutes or hours for instructions from Earth, so they need to detect and handle problems on their own. The Mars rovers are already semi-autonomous explorers. Future starships may navigate hazards almost entirely without human input. Now let's talk about something that changes the economics of everything: reusability. For decades, rockets were mostly expendable. You'd spend hundreds of millions of dollars, launch once, and drop the hardware into the ocean. Imagine if every flight on an airplane destroyed the plane. SpaceX and others are rewriting that script. By landing and reflying booster stages, they're pushing launch costs down dramatically. A fully reusable spaceship, like the Starship system aims to be, could lower costs further, enabling frequent trips to orbit and beyond. Reusability drives design choices: engine durability, heat shield robustness, landing legs, propulsive landing systems, and fast turnaround maintenance. It's not just rockets either. Crewed vehicles like Dragon, Starliner, and potentially Starship's upper stage are all designed for multiple flights. If humanity is going to build true spaceships, vessels that operate regularly like airlines, reusability isn't optional. It's the foundation for space infrastructure, from fuel depots to orbital shipyards. So what does a long-duration deep space ship actually look like? Probably not a sleek movie cruiser. Real designs are more like modular scaffolds, propulsion units on one end, rotating habitats for artificial gravity, large radiators for waste heat, and storage tanks tucked wherever they can fit. For Mars missions, concepts like NASA's Deep Space Transport or various private proposals use assembled modules launched separately and joined in orbit. Habitats might spin on tethers or in torus-shaped rings to provide partial gravity, reducing bone loss and muscle atrophy. Large radiators are needed to dump heat, because in space there's no air to carry it away. They often look like big flat panels extending from the ship. These ships wouldn't be designed to land, they're space-only vehicles. Landers and ascent vehicles would be separate craft, docked and undocked as needed. Think of them as ocean liners between worlds, with smaller boats handling the shore landings. Beyond Mars, things get seriously speculative, but still grounded in physics. One promising path is nuclear fusion propulsion. If we can harness controlled fusion, we could heat propellant or directly exhaust fusion products to achieve far higher exhaust velocities than chemical rockets. Fusion drives could cut travel times to the outer planets from years to months. Concepts like Project Daedalus and newer designs from research groups imagine massive, unmanned interstellar probes pushed by pulsed fusion. Even more extreme are antimatter engines. A tiny bit of antimatter annihilating with matter releases staggering energy, but producing and storing antimatter safely at scale is way beyond our capabilities today. There are also beamed propulsion ideas, giant lasers or microwaves pushing lightweight sails. These could accelerate tiny probes to a significant fraction of light speed at the cost of enormous infrastructure back home. None of these are ready yet, but they're serious studies, not pure fantasy, and they show what future spaceships might become. Then there's the elephant in the sci-fi room: faster than light travel. According to Einstein's relativity, nothing with mass can accelerate to or beyond the speed of light in normal space. That seems like a hard stop. However, certain mathematical solutions to general relativity, like the Alcubierre warp metric, suggest spacetime itself could, in theory, be manipulated. A warp drive wouldn't move you faster than light locally. Instead, it would contract space in front of your ship and expand it behind, carrying you along in a kind of bubble. The catch? These solutions require exotic forms of matter or energy with negative energy density, something we've never observed in usable amounts. More recent refinements have reduced the absurd energy requirements, but they're still utterly impractical. For now, real spaceships are limited to slower than light travel. That doesn't mean the galaxy is off limits. It just means interstellar journeys will either be robotic, multi-generational, or rely on technologies we haven't yet discovered or may never discover. Let's zoom out and connect the dots. Spaceships are not magic bullets, they're brutally constrained by physics. To leave Earth, you fight gravity and the rocket equation with giant chemical boosters. In orbit and beyond, you play the quiet chess game of orbital mechanics, burning precious propellant only when it matters. Inside the hull, life support, radiation shielding, and power systems turn an airless, radioactive vacuum into a survivable bubble of Earth. Guidance and control keep the whole structure pointed and stable, while reusability and modular design push us toward a true spacefaring infrastructure. Looking ahead, electric and nuclear propulsion will likely dominate deep space travel, with fusion and beamed sails as long-term possibilities. Faster-than-light ideas remain speculative, interesting mostly as thought experiments. If there's one key idea to remember, it's this. Real spaceships are tools, not toys. They're the hard-won result of countless trade-offs, built to do one thing humanity has never done before: turn the entire solar system into reachable terrain. If you've made it this far, your brain is basically pre-qualified for rocket science. Now don't let it stop here. The future of spaceships isn't only decided in government labs or billion-dollar companies. It's shaped by curious people who choose to learn, question, and build. If you enjoyed this deep dive into how spaceships really work, hit that like button so more people get this in their recommendations. Subscribe and ring the bell if you want more long-form breakdowns on space tech, from space stations and lunar bases to asteroid mining and interstellar probes. Drop a comment and tell me, what kind of spaceship should we cover next? A detailed breakdown of Starship's design, nuclear thermal Mars ships, or a full episode on realistic Starship interiors and artificial gravity? Check the description for sources, further reading, and some incredible free tools to simulate your own missions. Until next time, keep looking up, and remember, every great starship starts as somebody's wild idea on paper.